Hello, hello, hello. I have another cool tidbit I wanted to share with you, and it's actually using a multivariable chain rule to evaluate single variable derivatives. And so I think it's best to just consider an example here. Let's say we have f of x being equal to x to the x, and we want to find what f prime of x is. And there's two ways that are traditionally taught in Calc 1. The first way is to say, well, y is equal to x to the x, and so the natural log of y is equal to x ln x, and then you can find dy over dx from there. Or the other way is to say, well, y is equal to x to the x, which means y is equal to e to the x ln x, and you could differentiate both sides from there. Either one of those ways work, and they're both perfectly valid. But I think this way is even better. I think it's even less work. And mathematicians like to do the least amount of work as possible. So let's actually consider the multivariable function f of x comma y is equal to x to the y. Okay, so this is really equal to z. So what this is saying is that we're in 3D space, and so we have an x-axis, a y-axis, and then a z-axis, and they're all perpendicular to each other. This is x, this is y, and this is z. So we plug in an x here, we plug in a y, and we get out a z, or an f of x comma y. Just like how in 2 dimensions you plug in an x, and you get out an f of x, or a y. It's the same idea, just in 3 dimensions instead of 2. So we have one independent variable, which is z, and we have two independent variables, x and y. And so we have z. I kind of like to visualize it like this. We have a z, an x, and a y. Or let me do it the other way. We have an x and we have a y. Those are independent, and then they go to a z. How can we get to the z? Well, we can either start at x and go to z, or start at y to go to z. There's a finite number of combinations there. And so what I'm getting at is the chain rule is saying that the chain rule is saying that the dz by okay, let me think of this here. If I wanted to find dy by dx here, this is partial y with respect to x plus partial x with respect to y is the idea. So what I'm saying is that the total change dy over dx, so in other words, if I were to differentiate this implicitly, is the sum of the two individual changes with y, with respect to x when y is held constant, and with respect to y when x is held constant. That's what these partial derivatives mean. They mean, in this first case here, they mean you take the derivative of y with respect to x, so everything else is held constant. And then the second one means take the derivative of x with respect to y, so y is a variable and everything else is held constant. So with that in mind, dy over dx then is just nothing but we take partial y with respect to x. So here, x is a variable, and y is everything else is a constant. So x is a variable. So this, and maybe you're not comfortable with this at the beginning. So maybe you could say, well, y is a constant. I'll pick it to be like 2 or something. And so if it's x squared, it goes to 2x when we take its derivative. And in general, if it's x to the y, if y is a constant, then it just goes to yx to the y minus 1 by the power rule. So we can write that yx to the y minus 1. Now, for this piece here, now y is the variable and x is the constant. So this is maybe something like 2 to the x. When we differentiate that, we get 2 to the x natural log of 2. And if it's, oh, well, I really should make it a y. Yeah, okay. So, and in general, if it's x to the y, it goes to x to the y natural log y. So we add that plus x to the y natural log y. And in the single variable case, we are just considering the more general case of this multivariable function, and we're just, in the single variable case, we're just going to let x be equal to y. And so if we let x be equal to y, that would imply that we get x times x to the x minus 1 plus x to the x natural log of x, which is x to the x times 1 plus natural log of x. And that is the correct answer for the derivative of x to the x. And you can, I can show you that it does align. Let's do it the traditional logarithmic way. I'm going to say y is equal to x to the x, so natural log of y is x ln x, and then I can differentiate both sides. So 1 over y dy dx is, and this is why I like this method better, right? There's no implicit differentiation, there's no product rule, there's none of that. So we get x times 1 over x plus 1 times natural log of x, which is, that cancels, and we just get 1 plus ln x. So dy over dx is y times natural log of x plus 1, which is, y is defined to be x to the x, so x to the x times 1 plus ln x. And look at that, and look at that. They're the exact same thing. That's pretty cool. And you could do this with any single variable function, you know, if you want to try to get rid of the product rule, or you don't want to use logarithmic differentiation. It's a nice shortcut. It's a nice shortcut. It really just comes down to this idea. And I'll just say it once more. The idea is that the total change dy over dx is the sum of the individual changes when x is a variable and y is held constant, and when y is a variable and x is held constant. That's the idea. That's what the multivariable chain rule is saying in this particular example. And